But as you know, and I'm from Egypt. I have been working in ML research for the past 4 years. And last year I did a lot of cool projects at Meta, one of which is OPTR, which I'm happy to present today. And yeah, so this paper was actually presented at the reasoning workshop at ACL a week ago. And the paper is titled OPTR. Oh, actually, one second, I forgot that I didn't share my screen. Okay, yeah, so as I was saying, yeah, this paper was presented at the reasoning workshop at ACL last week. And it's titled OPTR, Exploring the Role of Explanations in Fine-Tuning and Prompting for Reasoning Skills of Large Language Models. So the R in the OPT stands for reasoning, if you couldn't tell. And the project was done in collaboration with Sidar Dirma, Pingyu, Jijing Jin, and advised by Asli Shilkimaz and Mona Diab. Also, please, let's make this talk interactive. So if you have any questions anytime, feel free to stop me and ask whatever you would like. Okay, so as you probably have noticed, there has been a surge in the release of large language models throughout the past year by both academic and industrial institutions. So here I just listed a few, and I should have probably added Llama 2, which was just announced yesterday, but you couldn't keep up with the progress, I guess. So those are just a few models that I mentioned, but in general, like we all use ChatGPT or any other language model. And I guess we're impressed by their performance on generating coherent text and their other capabilities. We've also been getting better and better results on reasoning benchmarks. And one prominent method that has been, let's say, a bit popular the past year is called chain of thought prompting. So yeah, I was saying that we all use ChatGPT and other language models, and we know that they're pretty good at like generating coherent text and whatnot. And we also know, like from the literature, that models are getting better in the reasoning benchmarks. However, actually, yeah, I was saying like one method that have been proven effective to elicit the reasoning capabilities of language models is called chain of thought prompting, which basically involves decomposing the answer into a sequence of step-by-step reasoning chains. So here's an example from the popular GSM-AK benchmark. GSM stands for Grade School Math. And as you can see, the model here is given an input, which says, Joy can read 8 pages of a book in 20 minutes. How many hours will it take her to read 120 pages? So the regular method, which was done before that, is the model is tasked to predict the answer directly, which is the answer is 5. However, with chain of thought, it basically tries to emulate the thought process of a human before it predicts the answer. So for example, here when if the model is prompted with or trained using chain of thought, it's going to say, in 1 hour, there are 3 sets of 20 minutes. So Joy can read 8 times 3, 24 pages in an hour. It will take her 120 divided by 24, which is 5 hours to read 120 pages. Therefore, the answer is 5. So as you can see, this method in general, like it boosted the results in reasoning benchmarks, and also many papers has come out since that try to explain why does it work, and that builds upon it, which I'm gonna mention briefly now. So to give you a sense of the progress we have seen throughout the last year, the original chain of thought paper reported a 33% accuracy on the GSM-AK benchmark when fine-tuning GPT-3. And the best result they got was 57% when prompting the PUL model, which is a 540 billion parameter model, using chain of thought prompting. Now, the current state of the art is 96.8%, which uses GPT-4 along with a combination of chain of thought, program-aided LM, self-consistency, model selection, and so on. And as you can see, this huge performance jump was just in almost a year. So we can see that the rate of progress is moving very fast. However, we still have some unanswered questions. So from a scientific standpoint, we still don't know, or we still don't understand why many of those aspects work. So the goal of this paper that we wanted to measure the role of explanations during fine-tuning and prompting and their effect on different reasoning skills. So here GSM-AK, for example, was measuring the arithmetic reasoning skill or mathematical reasoning. We wanted to measure its effect on other reasoning skills as well and see what works and what not. Of course, also there's the question of dataset contamination. It's generally a problem with evaluating GPT models because we don't know what they're trained on. So I mean, that will motivate our experimental design. So here you can see that we chose the OPT models to avoid any possibility of dataset contamination, since we know that the data used for pre-training. And since we wanted to measure the effect of fine-tuning on reasoning datasets with explanations, we fine-tuned different OPT models on the same datasets, once with and once without having explanations. So we call the fine-tuned models without explanation OPTR, and the ones with explanations OPTRE. And in the same vein, we wanted to measure the effect of prompting with explanation. So we evaluated the fine-tuned models on out-of-domain datasets, once by prompting with explanations in the in-context demonstrations, and once without explanations in the demonstrations. So we call those few-shot E and few-shot. We also evaluated the models zero-shot without having any demonstrations at all in the context during evaluation. And finally, we wanted to measure the results with respect to different reasoning skills. So we sampled 57 tasks from the supernatural instructions datasets, covering 26 different skills. So to quickly recap what I said, this is a figure showing the different dimensions used in this work. So there are 3 main dimensions, each containing 3 different levels. If you can see, for example, the fine-tuning dimension, we have 3 models, which is the non-fine-tuned vanilla OPT. And then we have the fine-tuned model without explanations, which is OPTR. And then we have the fine-tuned model with explanations, which is OPTRE. For the prompting, similarly, we have prompting without demonstrations, zero-shot, prompting without explanations in the context, which is few-shot, and prompting with explanations, which is few-shot E. So, and we also have 3 scales that we fine-tuned, which are 1.3 billion, 6.7, and 13 billion. And here, this different combination resulted in 27, like a grade of 27 different combinations, and each of which was evaluated on the 57 tasks of the supernatural instructions tasks. So maybe to give you a bit of sense for the fine-tuning, the datasets we chose them because those are the existing open source datasets that come with explanations for each sample, because since we wanted to fine-tune each sample with their corresponding rationale behind the answer, not only predicting the answer itself. So those datasets included the algebra question answering with rationales, also known as ACURAT, conversational question answering, common sense explanations, explanations with common sense question answering, also known as ECQA. And there is also the Stanford Natural Language Inference with explanations, the grade school math, proofwriter, and strategy question answering. So in all, those are 8 datasets. They're all covering different reading skills, and they all have an explanation before or after predicting the answer. And for the evaluation tasks, we used the supernatural instruction tasks. Those are almost more than 1,600 tasks, so we had to filter them down. And in order to filter them, we use a simple heuristic to get the relevant tasks up to this work. So one criteria we wanted to measure, which is focus only on tasks that contain a single reasoning skill. So some tasks, for example, can have something like social reasoning and mathematical reasoning at the same time, for example. So we didn't want that. We want to only measure atomic skills when we're reporting the results. Secondly, we want a task that can be evaluated using classification mode as opposed to generation, which I'll explain in the next slide. And finally, from the filtered set, we sampled randomly a maximum of 3 tasks per skill for the testing and 1 for the validation set. And the table on the right, which is you can see, shows all the 26 reasoning skills and their corresponding tasks used for testing. Okay, so this is the template that we use during both training and inference. So as you can see, we first have a task definition, followed by an instruction saying, provide your answer, followed by a brief reasoning. And then we have our in-context examples, which consist of input-output pairs. And finally, we have our input, then the options that the model chooses from, or should choose from, and then the output, which consists of a string that's a template string that must predict the answer first and then must provide the rationale or explanation after predicting the answer. So to be concrete, here's an example from Proofwriter, which is one of the fine-tuning datasets used in this work. So the task definition here is you are given a sequence of facts and rules followed by a question. The task is to answer the question using yes, no, or unknown. We then have the instruction and the in-context examples. And the input, for example, here for Proofwriter is a sequence of facts and a sequence of rules, and then a question in the end. So for example, here the facts are Charlie is white, Dave is furry, Fiona is quiet, Harry is nice, so on. And then rules, like if someone is nice, then they are round, all red people are white, brown, green people are red, and so on. And then the question is Harry round? So the model should be able to deduce from the facts and rules the answer. And here, for example, the answer is yes, because, and then should explain why that's the case. So here, for example, because Harry is nice, and if someone is nice, then they're round, therefore Harry is round. And here we did something that's different than the original Proofwriter paper, which we converted the implications to natural language statements, as you can see, instead of only focusing on the rules of the explanation. Okay, so going back to the evaluation method. So in a language models in general, there's like different ways for measuring performance. And in this paper, we chose to use rank classification, which was also used in the original GPT-3 paper. It means we measure the most likely output from a set of candidates. So to do this, we have to score each candidate using the log probabilities of the output conditioned on the input. So for example, in Proofwriter, we have 3 candidate answers, which is the answer is yes, the answer is no, the answer is unknown. Therefore, we use different scoring functions to calculate which candidate is most likely to follow the input. And the reason we chose classification is that the alternative, which is generating the answer and then doing exact matching, might be influenced by various factors, such as decoding strategy, decoding parameters, and the prompting method. So here it is better to capture the underlying classification method, in my opinion, is better at capturing the underlying reasoning capability of the model without having those other factors influencing the ability of the model to make the output surface in a way. And we did use different scoring functions to measure the log probabilities. So we actually experimented with 4. The first one is basically taking the average of the log probabilities of the candidate tokens, pretty straightforward. And then there's one called unconditional norm, which is we're taking the difference between the sum of the token scores, that is the log probabilities of the candidate tokens, when the candidate is unconditioned, and the sum of the candidate tokens when it's conditioned by an input. Then we have something called the suffix, which is only considering the token scores that's conditioned, and the sum is taking all the scores as passed to the model. So at each task, we evaluated using those 4 scoring functions, and then the result of the corresponding task is the maximum accuracy is the one that corresponds to the maximum accuracy across those 4 scoring functions. And let's start with the results. So I'll stop here first, and let's see if I want to see if anybody has any questions or anything they want to ask. Okay, if not, then I will continue. I also can't see the chat if anybody's sending anything in the chat, so I assume you're not saying anything. Okay, so again, this is a high-level view of the results, average across all of the 57 tasks, as a function of the 3 primary dimensions analyzed in the study, which is the fine-tuning, prompting, and scale. So as you can see here, there's a slight monotonic increase in the performance of each model as we increase the scale from 1.3 billion to 13 billion. And this is only under the two few-shot prompting conditions. In general, it indicates a positive correlation between the model's capacity and its overall performance. And here, which is the important, in my opinion, the important contribution of this work is that we are reporting the results on the granularity of the reasoning skill level. So in this table, we are showing the skills where the fine-tuned models, OPTR and OPTRE, perform significantly better than the vanilla OPT model, as measured by a Welch's t-test. And we can see, for example, that both fine-tuned models perform significantly better on the numerical, analogical, social interactions, and reasoning on objects, reasoning skills, while the model that's fine-tuned on explanations performs significantly better on the counting, physical reasoning, and textual entailment. So here, for example, we can deduce some, we can provide some insights on what skills actually benefit from those explanations. On the other hand, we also have skills that perform significantly worse than the fine-tuned models. So in this case, we have like the argument and common sense and deductive reasoning skills. Similarly, this is used, both tables are only measuring under the few-shot prompting conditions, which I'm going to explain later. And this table is a bit big, but we can take step by step. So here we're showing the fine-grained results on the level of the skill as a function of the fine-tuning dimension and the few-shot prompting method. So the first, it's divided into 4 blocks. If you can see, like there's a line dividing the table. And we can see that the first block shows the skills where the fine-tuned models, that is OPTRE or OPTR, outperforms the OPT model, the vanilla OPT. Then the second block highlights the skills where the OPTRE has better accuracy than the other models, therefore illustrating the importance of fine-tuning with explanations. And the third block shows where the vanilla OPT outperforms the fine-tuned models. So actually, fine-tuning here hurts the performance, as was seen in the previous slide. Then the fourth and final block shows the skills where the choice of model or prompting method has little impact on the performance. So here we can see that actually explanation doesn't affect the performance at all. And the cells, which are shaded with colors ranging from green to white, indicate exactly their position in the accuracy spectrum for each row. And we're highlighting have different shades of green to indicate the variance across the models, basically, to convey the extent of similarity of the scores between models. So this table, you can see it kind of provides an overview or a summary of our results. And a final question which we wanted to ask is the effect of the interaction between fine-tuning and prompting dimensions. So therefore, in this table, in the first column here, we actually measure the variance of the absolute difference in accuracy for each models across the different reasoning skills when using few-shot and few-shot E. So here, as you can see, it's the difference between prompting with explanations and prompting without explanations. So we wanted to see if there's any difference in both methods across the different models. So as you can see, for OPTR and OPTRE, the variance is quite small, which implies that the presence or absence of explanations in the few-shot demonstrations does not significantly impact the performance of the fine-tuned models. And the other two columns shows the performance, average performance across all tasks for the few-shot and few-shot E prompting methods. And we can see that there is a monotonic increase as we go from OPT to OPTRE and from few-shot to few-shot E. Okay. So now let's talk a bit about the limitations of this work. There are a lot of limitations, and it's important to acknowledge them. And the first one is we're here considering only a single language model, which is OPT. So further work is needed to see if the results generalize to other LLMs. with different architectures, pre-training objectives, or pre-training corpus. And secondly, we only use a limited set of reasoning datasets for fine-tuning because we relied on open source datasets that come with explanations for each sample. Thirdly, the experiments only cover a limited range of model sizes. Therefore, it's possible that the findings may not hold for larger models. And we only consider the few-shot prompting methods during fine-tuning. And it's like further work is needed to investigate the effect of having demonstrations during fine-tuning itself and compare it with the zero-shot prompting afterwards during inference. And to conclude this paper, we investigated the impact of incorporating explanations during fine-tuning or prompting of 3 different sizes of the OPT model, and we found that while explanations did provide a small improvement in performance, the effect was not significant when incorporated in the in-context demonstrations during inference for the fine-tuned models, as was measured by the variance across difference of both. And we also showed that the fine-tuned models exhibit significant improvements in reasoning skills, such as numerical, analogical, and reasoning on objects. And the fine-tuning with explanations helped the physical counting and textual entailment the most compared to fine-tuning without explanations. And finally, the goal of this paper is to offer insights into the effect of explanations on reasoning skills, as well as basically showing the skills that exhibit negligible or negative effects, as was shown in the previous tables. So yes, thank you very much for listening up to this point, and I'm happy to take any questions you might have and can open the discussion if you like. Okay, I can also share the slides again if you have any questions.
Hello, I did ask a question in the chat earlier. Can you hear me first?
Sorry, I didn't hear. I didn't hear this. Sorry, can you say that again?
Can you hear me now?
Yes, I can hear you now.
Yes, I did ask a question in the chat earlier. I was wondering, did you experiment with different templates in the beginning? Like, how was the effect of, for example, having the explanation before the answer?
Yes, we did experiment with different templates, and we actually found that having explanations before and after the answer didn't affect that much. We actually show an improvement for predicting the explanation after the answer in the validation set. That's why in the end we chose to go with that. But the results weren't that much, it wasn't that different to choose between that or that. So there's another question from in the chat. There are no consistent gains from fine-tuning models with explanation or prompting for different reasoning tasks. Sorry, maybe can you elaborate on the question more? Okay, so I'll read the question again. So someone is saying there is no consistent gains from fine-tuning models with explanations or prompting across different reasoning tasks. So if there's any deeper analysis on the relation between the type of task and fine-tuning approaches to find out when and why a specific approach fits a specific task. So in general, we didn't consider the type of the task itself. We only consider the labeled reasoning skill as they come by as labeled in the supernatural instruction tasks. The task itself, of course, they have different dimensions, like different domains and different types, as you said. So we only focused on the reasoning part, and we didn't cover the other types of the tasks, basically. If that answers your question. And yeah, thank you so much for making it to the talk and attending it.
Thank you for and thank you for the beautiful presentation.